Well, let's get started. We're going to start in chapter 1 of the book, Physical Science by Shipman, Todd, and Wilson. And one of the things I want you to do is that expect that you guys can do this. This is going to be something that you can make sense. Sometimes people at the parties or get-togethers will say, "Oh, I didn't get science. I don't understand math," and it's sort of a subject that people lightheartedly agree with. And I think that's the wrong thing to do. I think that every one of you can do this and get this and use it to your advantage, using the math and the science that we understand behind there. The biggest way you're going to be able to do this is just remain curious. Okay, as we kind of grind through these topics, sometimes it'll be a way that doesn't make sense because you haven't seen it before, and that's normal. Keep your notes, work through your homework, read broadly in and out of class as you're going. And things you like, I mean, that process is going to sharpen your mind. Find others which you can study with, find others in which you can talk about your field. Revisit your notes. It's not just enough for once. If you take my notes that are here as your basis from which, and you send those off to yourself or save them in your the online storage areas, that's fine. But revisit them and order them in the way you want. Put pictures online. Find ways to put images that help you remember what these processes are that we talk about. And last one, remember, it takes time to learn complex things. Most of my students that have worked in the last 25 years of teaching don't understand some of these new worlds. If we're talking about chemistry, it's a microscopic world you haven't maybe seen or trained yourself to think about. All these words may be new and you're confused about this, but with a little bit of time you start to recognize some of the words I'll talk about. Okay? You'll just say, it seems like a bunch of unconnected facts at first. Well, a little bit more time. You're going to start to understand those concepts, and you can do the problems if they're set up for you. After doing those for a little while, you'll start to become comfortable, and you'll understand that this, hey, happens outside in my street, in my water, my water treatment, water softener or something at my house, and we can talk about concepts where you'll see those. You'll start to get comfortable in a way that you'll eventually become intuitive, and so that you'll come into a room and say, something's not working, and I can explain those from a molecular perspective. Or I'm trying to get my car to work, and I can't get it pushed because it's too heavy for me to do those. And you'll say, I can understand some mechanical advantage of how to use my force to multiply that. All of these things are going to be in there, and I hope to get you down to this level. Science is just something that's fun and can be explored and applied every day of wherever you're at, in your job or at home, with friends or family, and it can be something quite useful. We have a list of chapters. We're going to start right away at chapter 1 here, in Basic Tools of Science, Scientific Method, how to deal with numbers, and then progress right on to 3 chapters in this first area that are going to be your first unit. How things move in the air like projectiles, how forces cause motion to happen, and buildings are held up by forces, energy, work, and momentum. So that'll be the first 2 weeks in our first test. This will be sort of its own little unit, and so the exercises there will be its own sort of small unit as we continue on. So let's move into those. The first thing is going to be in section 1-2 in your book, and I want you to notice that there is a method that up until really 300 years ago, science didn't progress quickly because people sort of took it haphazardly. Yes, there were absolutely kingdoms and times in history in which there was some effort to apply towards understanding science. A lot of it was military applications because it gave you a distinct advantage. So what we did come through is that in times there was people were out there and said, wow, I see something, and I noticed that today it's a little different. The only way that scientists have really come up to say, let's take a second to understand that better, because on something you really enjoy, is that they noticed what was different. That, of course, means you had to know what was regular. If I look outside the window and I see monarchs are coming by, if I didn't know that, wow, this is a little strange, it's really early for those to come by, you might have to ask yourself a question of why. Why does your car not work when you come out in the morning? Okay, maybe some of it's very familiar to you because you spend a lot of time with that, but you'll go through a process to say what's different about that. Now, the next step is you're going to propose ideas. They're like working theories. Okay, hey, there's 3 things that could be wrong with my car. Maybe it's the starter, maybe it's the battery, maybe I don't have any gas. In each one of those, you have to have a couple of ideas and not just stop there, not just one, I'm going to check one thing out, because then you got to go back to the beginning. But when you have a multiple array of ideas, you really can test them all simultaneously to see what your evidence of things you work with are supporting which of those ideas. It's tough to go down the wrong path of just one idea and not have a couple of things. That's where some of the craziest ideas have come from, is that they had a breadth of ideas to explain science, and they went into to then test them. Okay, once you have a couple of ideas of what is the issue that's different, then getting in and setting up an experiment to slowly check each one, change only one thing at a time to then exclude certain kinds of arguments, get your observations, and being very organized. Observations aren't really observations unless you can put them in a systematic place. Tables written out, graphs are even better because you can see your data. And nowadays, it's even more exciting, and part of my professional interest is to take scientific data and put it out on maps and GIS maps. Some of you may have had Ken Yanow, who teaches the GIS. Well, that's one of my specialties as well, is to putting scientific data onto maps. And so all of those areas and observations you made, we're putting them onto places so we can see patterns. And you get a lot of groundbreaking and new understanding by seeing how your data looks in terms of the real world around you. Last one's you're going to make conclusions, but you're trying to get back and answer this original note, what you noticed that was different. That process is the scientific method, okay? And that process is something that you're going to go through. Normally, you start off hypothesis, and that's not your best guess. It's like all the possible guesses, okay? And you're going to test those hypotheses. Those that come back with a time period of experience and support by several other people as well as yourself can be then maybe called a theory. After it's been widely tested, we'd call that a law. The reason that's important is if you're ever writing up scientific sort of work and putting into articles, this is a great sort of same process in which most scientific articles are written. You pose your question, give some sort of background of why it's important, where it will lead you into new discoveries. There might be grant writing, so if you were in a job and you wanted to pioneer some new technique in your area, you're going to describe what you're going to do to show that this is going to work. That money should come in to support you. Here's the data. Hey, I'm gonna work a new workflow around a shipping center, of which I'm going to show how we can get 10 times the volume of materials through. And this is the process I'm going to go. But I am going to need a little bit of money to buy 2-3 computers and some tracking devices, that kind of stuff. There you're going to then provide some interpretation once that data starts to come in, some graphs, you show your story convincingly, and if you conclude by answering that question, those that have supported you to do this are going to want to get behind you again. So that's a process that the science portion is really all about. Finding something new. Science isn't about memorizing what these books had been. The job of the scientist is to get out there and do something you've never seen before. Graduate school, every day we came in and I studied small molecules and the way they relined. It was about coal chemistry because I was from North Dakota. And we put metals on there, and what we wanted to see is how to break them up or make them more reactive so we can make more products, make that coal that we had into something other than fuel, medicines or catalysts or other ways that could serve us. So that process had to be followed, and that's what actually paid for my graduate school when we did those things. Now, one of the ways that we're going to be able to do this is using numbers, and that's what this whole first chapter is really about, using numbers in a little bit different way than what you've maybe used in math. Math comes out with these great answers and graphs that cross right at one single point. And the reality is that numbers can be a little bit different. And a couple of those ways that they're different is that, one, we're concerned about how accurate you were when you measured something. A lot of times, a lot of stuff comes through. If you're dealing with, like I say, I know you guys are in San Diego, a lot of shipping kinds comes through. You got millions of tons of sort of material, and you just have to make your best guess on a big scale or on the numbers of objects that come in. And so that accuracy is important when you communicate in a manifesto what has been shipped in. I have to tell you how well do we know that number as well as just what that number is. Another thing in science is we measure huge things and small things, and so the scale, atoms are super small, 1.4 billionth of a meter. Whereas the distance to the next star, if we're going to put people on Mars, for instance, it's going to be millions and millions, tens, if not 20s of zeros. So we need to deal with them in a way that doesn't become cumbersome. And the last couple of things that I want to mention are that the units that we use are always just as important as the number. You know, if we start to send things in the United States, as far as the metric system is the one country that doesn't use the metric system and all the rest do, and we send something that goes across in inches or even yards, let's say, and you assume that when the person receives it was meters, they're pretty close, but 3 inches for every meter you have could make a catastrophic difference, and sometimes it has. So the last one is that this idea units are going to become important, and how do you deal with those, how do you manipulate those, and the last one is that that measurements are going to have direction. When we talk about speed or energy, it's not only just, hey, I'm doing 50 on the highway, I'm doing 50 miles an hour east. That direction is going to become important. And all four of those things, we're going to have to learn some different techniques to deal with.